Alrighty, and with that, good morning everybody. Welcome back to Linear Algebra. Plan for today, we're going to wrap up Standard 9 by talking about some properties of isomorphisms between vector spaces. My next office hours are on Monday after class and from 1 to 2. Since we already took the Standard 9 quiz, we're just going to jump right into Standard 10, I mean double digits, on Monday, where we're going to be looking at determinants of matrices and what do they tell us? What sorts of useful information can we gain? Pass back exams. Nice job on the exams. They all did really well. Standards 8 and 9, I admit, were tough questions on the exam. I posted solutions on Canvas, so I encourage you to check those out if there's something you're unsure about, and or to come by, and I'll be happy to talk with you in office hours. I still am a little bit behind on grading retests, so if you took like a retest yesterday, for instance, I still haven't gotten to it. I'll get caught up with grading those over the weekend. And also, over the weekend, I will update everyone's mastery totals on Canvas, because I have not updated those in the last week, so those will be up to date. And I'll send an email out or remind you on Monday when that happens. Any questions or comments before we get started for today? Yes?
How many standards are we going through for the entire course?
12.
12.
Peaches.
Does that mean that if I get 23 masteries, it's an A?
No.
What?
I don't know what it means. I still have to go through and evaluate that. Any other? Yes?
So I think before it was, I don't remember what like update tool was, but it was something like 18 out of 20 was like an A. So basically if it's like, it's 12 students now, would that be like 10 out of 12 or something?
I need to go back and scale it, and I'm not going to answer these sorts of questions today.
Okay.
I will let you know when I've rescaled everything and updated the syllabus accordingly. Okay, so vistas. So a statistics professor one day decides to offer a 50-question true-false exam. But it's not a bad idea. So gets it to the exam, gives students 2 hours. There's one student who sits at the back of the lecture hall who keeps flipping a coin and writing down an answer. Flipping a coin, writing down an answer. He keeps doing this for full 2 hours, long after everyone else is done. So the professor goes up to the student after the exam. She says, look, I know you haven't studied for the exam. You've just been flipping a coin to determine whether you're writing the answers true or false. But what I can't figure out is why is it taking you so long? The student glares at the professor and says, shh, I'm checking my answers. Okay, so if we think back, do a quick bit of review from Monday's class, because Wednesday was the exam. Monday, we had started to talk a little bit about what does it mean to form an isomorphism between vector spaces, where an isomorphism is a function that goes between your 2 vector spaces that is linear and it is invertible, meaning it's 1-to-1 and onto. It has sort of an inverse function that goes backwards. And what we said is that if you can find an isomorphism between your 2 vector spaces, then V and W are called isomorphic as vector spaces, which we kind of denote by this V squiggle equals W. And the main idea behind isomorphisms is that if you have 2 vector spaces that are isomorphic, that's mathematically saying they behave the same way, that they may superficially appear to be different from each other, but doing kind of different types of algebraic operations inside of one is going to be like doing different types of algebraic operations, etc., inside of the other. And mathematically, they're the same if we can find one of these isomorphisms between them. And I think as an example, let's see, what was our example last time? We had something like, take a function from 2x2 matrices to R4, where we take f of the matrix A, B, C, D, and map it to the vector A, B, C, D in R4. And we said that that was an example of one of these isomorphisms. It's linear, It's 1-to-1, no two input matrices map to the same output matrix, and it's onto. Every vector in R4 is going to get mapped to by some matrix. And the fact that we can find an isomorphism from 2x2 matrix land to R4 tells us that the vector space of 2x2 matrices and the vector space of vectors in R4 are isomorphic, meaning elements in one vector space may look a little different than elements in the other vector space. One is 2x2 matrices, one is just column vectors, but mathematically they behave in much the same way as vector spaces. We could say things like they have the same dimension, they have the same number of elements. If you do an operation in one, it's like doing an operation in the other with the corresponding vectors. So mathematically, they are the same. And what I want to focus on today is trying to prove some properties of these sorts of isomorphisms in general. So with that in mind, does anybody have any questions or comments related to isomorphisms before we jump into the new stuff? Groovy. So with that in mind, let's prove our first property. So first property is going to be if we have a vector space V where V has dimension of n, it's an n-dimensional vector space, then V has to be isomorphic to Rn. In other words, if you're looking at any n-dimensional vector space, like vector space of 2x2 matrices, you're always going to be able to find an isomorphism, one of these 1-to-1 onto linear functions that goes from your vector space to Rn specifically, R4 in this case. So let's see if we can prove that. So let's suppose that we have a vector space V where the dimension of V is equal to n. We're going to prove this in generality. Refresh my memory. What does it mean to say that a vector space has dimension n? Like, what does that tell us about the vector space? I see we're going to have one of these classes, aren't we? Well, why do we know, for instance, that the dimension of this vector space is 4? What about this vector space relates to 4 somehow? Isaac?
You have 4 total entries.
You have 4 total entries, which tells us what? Specifically, if you were to try and form a linearly independent spanning set or a basis for your vector space,
You need 4 individual vectors.
yeah, we need 4 matrices to kind of form a basis for 2x2 matrices, like 1, 0, 0, 0, 0, 1, 0, 0. I'm too lazy to write out the other 2, apparently. 0, 0, 1, 0, 0, 0, 0, 1. So in particular, when we say that a vector space has a dimension of n, what we really mean is that any basis of your vector space has exactly n vectors in it. That any basis is going to have n elements to it. So let's define a basis. We're going to let V1, V2, up through Vn be a basis for V. So we're going to have a set of vectors V1 through Vn that span the vector space and that are linearly independent. None of them is a linear combination of the others. And here we're going to use a result that we talked about several standards ago. Haven't really used very much since. Do y'all remember when we were talking about Rn that we said if you have a basis for Rn, then any element in Rn can be written uniquely as a linear combination of those basis vectors? Isaac does, I'm glad. We're going to use that result here. So So just to give you a reminder, you can say since S is a basis for V, any element little v in V can be written uniquely as a linear combination of basis vectors. Or in other words, what that means is that if we wanted to try and find constants, so that little v equals C1V1 plus C2V2 plus CnVn, there's always going to be one set of constants, C1 through Cn, that'll get the job done. So this is going to have a unique solution, C1 through Cn intervals. And because that's sort of an abstract thing to think about, I thought we could kind of go back for a second and look at a quick example of what this theorem is telling us. So let's say we want to look at R3. And turns out this set of three vectors is a basis for R3. It's a linearly independent set that spans all of R3 when taken together. So what I would like to do is I've picked out a random vector in R3, 6, 9, negative 12. Maybe not random, but also not anything in particular. And what I would like to do is I'm going to try to find a way to write 6, 9, negative 12 as a linear combination of these three basis vectors. So in other words, I want to find scalars to put in these blanks. So if we take scalar 1 times 1, 0, 0, plus scalar 2 times 0, 2, 0, plus scalar 3 times 0, 2, 3 will give us 6, 9, negative 12. So Lana, what scalar do you think would have to go in front of the 1, 0, 0 vector?
6, 0.
Yeah, I think plain old 6. Because if we take 6 times this, then no matter what these scalars are, the first coordinate of the sum is going to be 6, right? Peaches, what's up?
Oh, I was waiting for you to ask for number 2.
Well, you're going to have to keep waiting, Peaches, because I'm going to ask you for number 3. What does it go in the third line?
Negative 4.
Negative 4? Yeah, to make the third coordinate check out, because 6 times 0 plus who cares times 0 plus blank times 3 is negative 12. The blank needs to have a negative 4 in it, right? Brooke, how about the second blank? What scalar multiple of 0, 2, 0 do we need to take here?
17 halves.
17 halves? Well, let's see. For the second coordinate, if we take 6 times 0 plus 0, plus 17 halves times 2 is 17. Minus 4 times 2 is negative 8. 17 minus 8 does in fact give us the 9. So I think it is 17 halves. So what this means is we were able to find scalars that make it so we could take a linear combination of these three vectors and get 6, 9, negative 12. And the fact that these three vectors formed a basis for R3, what that tells us is that these are the only scalars that will get the job done. There's no other scalars we could have plugged into these blanks to get 6, 9, negative 12. In fact, even if I'd given you a vector like, say, pi e 100, there would have been, and tried to write that as a linear combination of these three things, there would have been exactly one number to plug, or one set of numbers to plug into these three blanks that would give you pi e 100, for instance. And that's coming from this property that we proved several weeks ago, that if you have a basis for your vector space, every element in your vector space can be uniquely written as a linear combination of basis elements. I mean, there's only one set of scalars that'll get the job done. Technically, but Dr. Gerstle, technically didn't we prove this just for Rn? How do we know this works for an arbitrary vector space? technically you're right. When we proved this here, and we proved it when the vector space was Rn specifically, it turns out it works in general. But basically the same logic. So I don't feel like going back through and reproving the results for a general vector space, because it's basically the same proof. You're in okay so far? So, Dr. Gersel, what are we going for here? We're trying to show V is isomorphic to Rn, right? So what I want to do now is I want to define a function f that goes from the vector space V to Rn. And what I need to do is I need to somehow find a way to take in a vector V from this arbitrary vector space of dimension n and have it spit out somehow a vector of n scalars in Rn. So how can we do that? Using what we've defined so far. How can we find a way to take in a vector V and spit out n different scalars that'll give us a vector in Rn corresponding to the input V? Well, I would argue, if we look at what we've done so far, we've found a way to take an element little v in our vector space and have it correspond somehow to n separate scalars. What scalars do we have, Isaac?
C1 through Cn.
Yeah. This is a way of taking, yeah. So we know we can write V as a unique linear combination of V1 through Vn. We can take our little v and write it as C1 V1 plus C2 V2 up through Cn times the Vn. So how can we get n scalar values out of that? Just take C1, C2 up through Cn. And that gives you a way of taking a vector in element in the vector space V and spit out a vector of scalars that lives inside of Rn. So, like for instance, if we were to look at this example, we could define a function f from R3 to R3. That what it would do is it would take in a vector like 6, 9, negative 12. It would figure out how can you write a 6, 9, negative 12 as a linear combination of basis elements. And what would this function spit out? Well, it would just take these scalars that it found. 6, 17 halves, negative 4. So in other words, we're taking a vector in our V, an element in V. In this case, our V is also R3, and the V we're taking is the 6, 9, negative 12. And what we find out, how can we write V as a linear combination of our basis elements, which we already did, or you all did, I should say. And then we just take the scalars that we find in this equation, we put those into a vector in Rn, and that gives us a way to go from our vector space V to Rn by taking in a vector in V and spitting out the scalars that give you that linear combination of basis elements. Anybody have any questions or comments about what's going on there? So Dr. Gersel, what's up with this function f? Why would you define this f in such a weird way? I'll tell you why. Turns out this f has some nice properties to it. It's linear. This is a linear operation. F of v1 plus v2 equals f of v1 plus f of v2. And f of scalar times v is f equal to scalar times f of v. It's 1-to-1. No two inputs map to the same output. mainly because of this unique way. If we had f of v1 equals f of v2 equals, say, 5, 6, 7, 8, as an example, well, that would tell us that v1 and v2 are both equal to, or let's not use v1 and v2, let's use a and b. If f of a and f of b were both 5, 6, 7, 8, that would imply a and b were both equal to 5v1 plus 6v2 plus 7v3 plus 8v4, which would tell us a and b had to be equal. So no two inputs, in other words, map to the same output. And finally, f is onto. If you gave me a vector in R, let's say R3 for instance, over there, like 5, 7, 100, well, I can just say that's going to get mapped to by 5v1 plus 7v2 plus 100v3. Every vector in Rn gets mapped to by this function. So if we know our function f is linear, and it's 1-to-1, and it's onto, what does that tell us about our function f? What do we know about functions that are linear, 1-to-1, and onto? Michael, it's invertible. It's invertible, and more specifically, it's an isomorphism. Yeah, because that was our definition of isomorphism, is a function that's linear, 1-to-1, and onto. Invertible just needed the 1-to-1 and onto. For isomorphic, we also needed the linearity. So f is an isomorphism. And well, what does that tell us? We found an isomorphism from V to Rn, thus V is isomorphic to Rn. Any questions or comments related to that? I need Lincoln here so he can ask me a question that'll take him like 2 minutes to get out, and I'll still have a hard time understanding what he's trying to say. Now I'm being a bully. Like Lincoln's a good guy. He does have a hard time putting his thoughts in words sometimes. So, what does that tell us? It tells us any n-dimensional vector space is isomorphic to Rn. So for instance, if we wanted to take the vector space of all polynomials of degree less than or equal to 31, well, that's a dimension 32 vector space. So that's going to be isomorphic to R32 by this theorem. But this theorem tells us we don't have to go looking for a specific function. We know there's going to be a linear 1-to-1 onto function that tells us that polynomials of degree less than or equal to 31 as a vector space mathematically behaves the same way as R32 does. Thank goodness we don't have to find an explicit function from one to the other, because that would be a long, complicated function. Having to define how does it react to 32 different parameters. So let's prove another theorem. And this theorem is a little bit less abstract. Turns out we can show my chalk go. We can show that Dr. Gersel runs out of chalk very quickly in this class. Let me go get another piece of chalk. I'll be right back. I'm back. So next thing I want to do is I want to find an equivalent condition showing that a linear transformation is an isomorphism. And so what we're going to do is we're going to show that a linear function F going from V to W is an isomorphism if and only if the kernel of F is trivial, meaning only the zero element in V maps to the zero element in W, and the image of F is all of W. So in other words, you can determine, if you have a linear function, you can determine whether or not it's an isomorphism, meaning you can determine whether or not it's invertible by just looking at what's the kernel of your function and what's the image of your function. And if you know what those two things, if the kernel is trivial and the image is all of W, that's enough to tell you you got an isomorphism. Is that a stretch or a hang?
Sorry, I'm just stretching.
That's fair. I can just get stretches. I'm mainly going to be interested in proving the backwards direction of this. I want to show if the kernel is trivial and the image is all of W, then F has to be an isomorphism. So let's do that. Let's suppose that F is linear. The kernel of F is trivial, meaning only the zero element in V maps to the zero element in W, and we're going to assume that the image of F is equal to W. And I'm going to show F is invertible, which would tell us F is an isomorphism. Well, right away, if we know that the image of F is all of W, what property does that tell us that F has to be? If we know that the image of F is the entire codomain, if every element in W gets mapped to by something in V. Brooke?
Is that on too?
That is in fact onto. Yeah. So we sort of get onto for free. The one that's going to be a little bit more challenging to prove, that's going to take us a little bit more work, is we also want to show that F is a one-to-one function as well. So how do we show something's one-to-one? Or maybe, what does it mean to say that a function is one-to-one? Kind of looked at several examples of this, but now we're going to need to use it in kind of as part of our proof. What does it mean to have a one-to-one function? Beaches?
No two elements in the domain map to one element in the codomain.
Yeah, no two inputs map to the same output, in other words. That if I have an A and a B, or a V1 and a V2, in big V, if f of little v1 equals f of little v2, then v1 has to be equal to v2. If we can show that that's true, then that would prove f is 1 to 1. So let's do that. Let's suppose we know that f of v1 is equal to f of v2 for some little v1, little v2 elements in big V. And our goal is going to be to show little v1 has to be equal to little v2. Well, if f of v1 is equal to f of v2, then what would we get if we subtract f of v1 minus f of v2? Canada?
0.
We're going to get 0. Oh, which 0? The 0 element in V or the 0 element in W? So think about it this way. Where do f of v1 and f of v2 live? Do these things live inside of big V or do they live inside of W?
W.
Yeah, because little v1 is in V, but f of v1 and f of v2 have to be elements in W. So the 0 element in W is going to be equal to little f of v1 minus f of v2. How can we write this as f of a single expression? Instead of taking f of two different things, f of v1 and f of v2, and subtracting them, how can we just write this as f of a single expression? Michael?
F of V1 minus V2.
Like that?
Yeah.
Yeah, we can totally do that. What tells us that these two expressions are going to be equal to each other? Because there's a lot of functions for which you can't do that.
It's linear, right? So
Yeah, exactly. So the fact that we can do this comes from the fact that f is linear. If f wasn't linear, we couldn't necessarily say that. But the fact that f is linear tells us f of one thing minus f of another thing is f of first thing minus second thing. So, since f of v1 minus v2 is equal to the 0 element in w, what does that tell us about v1 minus v2? If it's something that when we plug it into our function f, we get 0, what does that tell us about v1 minus v2 if it's an element that we can plug it into the function f and get 0?
It's in the kernel.
Yeah, exactly. By definition, that means v1 minus v2 is in the kernel of the function. Because the kernel, by definition, is just the set of things that map to 0. Well, if v1 minus v2 maps to 0, then it has to be in the kernel, by definition. But what do we know about the kernel of f? Or what are we assuming about the kernel of f? I wasn't asking you. Jesse, what do we assume about the kernel of f as at the beginning of the backwards direction?
That 0 is the only thing that exists in the kernel?
Yeah, that it's trivial, that the 0 element in v is the only thing in the kernel. So what does that tell us about v1 minus v2 then, Jesse?
That it's
Leslie? Yeah, exactly. We could say, well, since the kernel of f only contains the 0 element of v in it, there's nothing else in the kernel, that was one of our assumptions. Well, if v1 minus v2 is in the kernel of f, that's going to tell us v1 minus v2 is equal to 0. And Kopeny, shaking your head. If v1 minus v2 is equal to 0, what does that tell us about the relationship between v1 and v2? Yeah, they have to be equal. You can just add v2 to both sides of this equation, and that tells us that v1 has to be equal to v2. Which is what we were hoping to show. Because we showed that if f of v1 equals f of v2, it has to be the case that v1 is equal to v2. What does that tell us? Well, therefore, f is 1 to 1. That's what it means to be 1 to 1. If f of v1 equals f of v2, then v1 equals v2. So we know f is 1 to 1. We also know that f is onto. We also assumed f is linear. And then, if we know that f is linear, 1 to 1, and onto, what does that tell us about f?
it's invertible.
It is invertible, but more than that, if it's
isogynous. Oh, sorry.
that is partially correct, the right word I'm looking for. It's an
Isomorphic.
yeah, it's an isomorphism. Isogynous. Is that like misogynist?
I think it was from a different class.
Okay. Fair enough. Say isogynous. I don't think I've heard that before.
We should change it.
I should do what?
We should just change it. We should just call it.
Isogynous? I don't think I'd be able to do that with a straight face. I'm sorry. The forward direction is fairly similar to show if f is an isomorphism, then it has to have a trivial kernel and resolve it.
Our proof for the part that v1 minus, like v1 is equal to V2.
Mhm.
Does that prove that V1 has to equal V2 or just that it can?
It tells us that it has to be. Well, from here, if we add V2 to both sides, what it would tell us is that V1 minus V2 plus V2 is equal to 0 element in V plus V2. What do we know about the 0 element in V plus V2?
It's V2.
Yeah, that has to be V2 by definition of what the 0 element is. 0 element plus anything equals that other thing. And then on the left-hand side, the minus V2 and the plus V2 have to cancel out, and we're just left with V equals V2, V1 equals V2. So it is a has to be and not just it can.
Thank you.
Technically, we're doing a lot. I'm not explicitly saying it, but we're using a lot of those 7 properties of vector spaces from the first page of the standard 10 packet that said, oh, vector spaces behave a lot like Rn. We're using a lot of those properties as kind of part of this process. Things like every element has a negative. If we didn't have that property of vector spaces, we couldn't necessarily say anything about V1 minus V2 because minus V2 wouldn't even exist. So, Neato Dorito. So, if we have a linear function, we know if it's an isomorphism or not just from looking at the kernel and the image. Excuse me, Zach, now I'm doing it. Here's a cool corollary of this, and this one's not in the packet. I forgot to actually include it in the packet before I printed it out, but it's kind of a fun little result you can say. If A is an n by n matrix, then, and let's say the function f from Rn to Rn is given by f of vector x equals a times x. So we're defining a function that's just literally multiplying by matrix A. What this theorem tells us is that f is an isomorphism if and only if A is invertible. Meaning A has an inverse matrix. So, in other words, this gives us yet another, like, what are we up to now? Like something like a 10th equivalent condition to saying a matrix is invertible. Along with, is that the function that is multiplication by A gives us an isomorphism. So why is that? Well, if you recall way back to standard 5, I think it was, we said, we proved in standard 5 that a matrix A is, an n by n matrix is invertible if and only if the kernel is trivial and the image is all of Rn. Well, according to this theorem, kernel being trivial and image being all of Rn are equivalent conditions to saying that your function is an isomorphism. So in other words, if A is invertible, then multiplication by A is a function that is 1-to-1 and onto. But if A is not invertible, then it's not going to be both 1-to-1 and onto. So toss that on the stack of conditions that are equivalent to A is an invertible matrix. Just print out a list of all the ones we have at some point. All right, y'all ready for the last theorem of today's class? This is the fun one. So it turns out that, so this theorem that I just erased the proof of says that if you have an n-dimensional vector space, then it's isomorphic to Rn. But what you can also say is that if you have two vector spaces that have the same dimension n, then they have to be isomorphic to each other, and not just Rn. So if V and W are both finite dimensional vector spaces. Finite dimensional meaning the dimension is finite. We don't have a dimension of infinity like we did with R infinity or the set of all functions from R to R. Those are infinite dimensional vector spaces. We're looking at things like Rn or polynomials of degree less than or equal to 8, stuff like that. If V and W are both finite dimensional, then V is isomorphic to W if and only if the dimension of V equals the dimension of W. So in other words, for two vector spaces to be mathematically the same, meaning there's an isomorphism from one to the other, all that you really need is that they have the same dimension. Which would tell us things right away, things like, Annabelle, what's your favorite 16-dimensional vector space? 4x4 matrices it is.
Okay.
So that has a dimension 16. And if we take another 16-dimensional vector space, like say, polynomials of degree less than or equal to 15, according to this theorem, these are mathematically the same as vector spaces, even though they have superficial differences between them. One has matrices, one has polynomials, but mathematically they behave in all the same ways, according to this theorem, since they have the same dimension too. So let's prove this. This is a fun one. I like this proof. Let's prove forward direction first, that if V is isomorphic to W, then the dimension of V is equal to the dimension of W. So let's suppose V is isomorphic to W. So what does it mean to say these two vector spaces are isomorphic? Well, it means there's a function from V to W that's an isomorphism. Then there exists an isomorphism F going from V to W. So I want to somehow say something about how the dimension of V has to be equal to the dimension of W. Well, what do we know about the dimension of V? We can relate the dimension of V to properties of F by saying the dimension of V has to be equal to the dimension of the kernel of F plus the dimension of the image of F. That if we add up kernel of F's dimension, image of F's dimension, we should get the V's dimension, the domain of our function. What result tells us that the dimension of V should be equal to the dimension of the kernel plus the dimension of the image? Isaac?
The rank nullity theorem.
Yeah, so in other words, we're just using the rank nullity theorem here. So what do we know about the dimension of the kernel and the dimension of the image? Quite a lot, actually. Because we're assuming F is an isomorphism. So if F is an isomorphism, Michael, what do we know the kernel of F is going to be equal to?
Is 0, the 0 vector.
Yeah, it's going to be the trivial vector. Technically, the set containing the 0 vector. But yeah, that's the right idea. And what do we know about the image of F? What should the image of F be equal to, Annabelle?
It would be the, I don't know, it should just be W.
Nicholas? Yeah, it's going to be all of W. We have a function F from V to W that's an isomorphism. So according to this theorem that we proved over here, that means the kernel of f should just be trivial, and the image of f should be all of w. That's what we proved in this theorem. Zach, what do we know about the dimension of the trivial vector space?
I have no idea.
Gadzooks. Phone a friend.
Peaches. 0.
Yeah, we said that if you just have the zero vector and nothing else, we call that a zero-dimensional space. All right, Zach, answer me this one then. What do we get if we add 0 plus the dimension of w?
0. The dimension of W.
That's the one. Yeah, it's just going to give us the dimension of w. So that tells us the dimension of v has to be equal to the dimension of w. We're running a little low on time, so I'm not going to write a formal proof of the backward direction. I'll kind of draw a picture to help illustrate what it means. So if the dimension of v is equal to the dimension of w, how do we know that v and w have to be isomorphic? Well, I think the idea is if the dimension of v is equal to the dimension of w is equal to, say, n, Brooke, if v has dimension n, what do we know that v has to be isomorphic to?
Rn?
Yeah, Rn. That was the first theorem we proved today. So v has to be isomorphic to Rn, and w has to also be isomorphic to Rn. So let's draw out a little picture here. So this is v, this is w. We're going to get a function f from v to Rn that's an isomorphism. We're going to get a function w from w to Rn that's an isomorphism. Let's call it g. I want to somehow construct a function that goes from v to w. How can we find a path from v to w using this picture? Peaches?
F and then inverse G.
Take f from v to Rn and g inverse from Rn to w?
Yeah, true.
How do we know g has an inverse?
One of the theorems.
Oh, well, one of the theorems.
Yeah.
Well, we know g's an isomorphism, and part of this is less a theorem and more of a definition. But part of the definition of isomorphism is you got to be invertible to be an isomorphism. So g's invertible, so we can take an inverse, g inverse, and then it turns out g inverse composed with f, if we do f and then g inverse, is going to give us a function from v to w that is an isomorphism. So if f is an isomorphism and g is an isomorphism, then we can just do f and then g inverse, and that'll give us an isomorphism from v to w. I'm skipping a lot of details here, like for instance, if g is an isomorphism, then g inverse is an isomorphism. If f and g inverse are both isomorphisms, then doing one and then the other is an isomorphism. There's a lot of details to fill in. If you take, like, say, discrete math, you get to fill in all of these details by proving these sorts of properties. But I think that's going to do it for standard 9. On to double digits. So on Monday, when we come back, we're going to talk about standard 10, where it's all going to be numbers again, for those of you who are scared of all this abstract stuff. How do you take determinants of n by n matrices, and what does that have to do with invertibility of the matrix? Because we're going to need that to talk about our final major topic of the semester, which is eigenvalues and eigenvectors. Have a good one, everybody. See y'all on Monday. Can you do it like right now?
Yeah.
Yeah, sure. Meet me outside my office. I'll be right down. Okay.
So on here,
Yeah. I've got like,
Why? Isn't
oh, I think it's 7, I don't remember it's 7.
pretty low?
Because F is not an isomorphism.
With,
Can I show you something?
Yeah.
So I can give you, the idea of why is F not trivial is there's lots of vectors that'll map to 0 here. Let me just write it down just real quick so I remember it. You're right that the 0 vector is in here, because if you plugged in the 0 vector for A, B, C, and D, you can get 0 as an output. But I can also think of other vectors in here that'll map to 0. So, for instance,
When I was in 6th grade, on the side of the 10th grade, every day at 10 from school. And so we do every day at 10 from school.
that also maps to 0, right? Because you get 0x cubed plus 1 plus 0 minus 1x, which comes out to 0x.
Yeah.
I can also do this. Turns out,
Wait.
Oh, okay, got it.
yeah,
Sorry.
yeah, it turns out the nullity ends up being 2 here, because you can have these two vectors will form a basis. And probably the easiest way to do this problem is actually to use rank nullity and say that the image of this function is going to be 2-dimensional. And then since the domain is 4, 4 minus 2 equals 2.
Yeah.
That's probably the easiest way to do it if finding the nullity directly is a joke. Oop.